Okay, let's study how to train a simple artificial neural network in this lecture. The training is based on two procedures. The first one is feed-forward calculation of a neural network, and second is a backpropagations to minimize errors using a gradient descent method. The gradient descent method. Gradient descent method. We're going to study that today in this lecture. And we have a observed data sets here where we have a diameter and corresponding price in KLW, and we have a diameter 600, 700, 800, 900, 1000 diameter of circular columns. Circular columns. This is a fictitious data, but we'll assume this is a observed data. That means if we have a 700 diameter, we're going to have a 300,000 KLW price, and so on and so forth. So we have 1, 2, 3, 4, 5, 6, 7, 8. This is 8 data sets. But this could be a big data set if we have a more than maybe a few thousand, 10,000, 100,000. So this is equivalent to big data sets in real cases, but we just take 8 data sets to explain in this lecture efficiently. If you see the graphs here for given dimensions of circular columns, the corresponding construction cost is plotted in y-axis. So we can see the trend of the big data. We'll call that this is big data, even though this is small enough. So we have trend that looks something like that, right? So this is a kind of visualization of observed data sets. But here we divide the data into two subsets. One set is for training networks and one set for testing the results of trainings to see if the training are performed accurately. So this 5 data is used for training data, and 3 data are used for testing the trained data. So if you see over here, the red dot represent a training data, whereas a blue dots represent a testing data. So we train this data based on red dots and test based on blue dots to see if your training are performed accurately. This is very important. So the same data is divided into training and testing so that the neural network will not see this data. The neural network only sees the training data to be able to find out the input-output relationships, or just by mapping inputs to outputs. This is what we're going to do. So here we have a initialization of feeding line, which means that we have a initial feeding lines from which you can start mapping or fitting or matching input data sets to output data sets. If we use a linear lines to fit price and dimensions of columns or diameters of columns, we're going to use this formula. The price equal the slope, let's say ax plus b. So the x is a diameter of the circular column, p is price of course, and a is then slope of the curve that we are initializing or using for fitting this input and output data, and b is y intercepts here. So A here, I'll say slope, and B, I'll say intercept, y-intercepts. If you see over here, slope and y-intercepts. So we just assign any value, initial value. We call the initialization of fitting line. 0.1 for weights, that's the slope of the curve that you are initializing, and bias is equal to 200. So this is a random number. It could be any number, randomly assigned. It could be any number randomly assigned to initialize your. So if you go and explain one more time, it could be any randomly assigned number, so that you can initialize, or you can set up a linear curve to start with fitting or matching or mapping together relationships between input parameters and output parameters. Then we call this process initialization of fitting line here, assuming a randomly assigned numbers for slopes and intercepts. You assume this linear line as your starting initialized curve, starting initialized equations. For example, the price equal 0.1 times diameter of the column plus 250.